Hello, welcome to another video. And so in this video, what we're going to do is we're going to go over force examples. So we're going to go over kind of intro force examples, normal force, an elevator example, which is, just a normal force example, but with a moving system, and then what pulling a box kind of looks like. Okay. Um, so here's example one. It looks like a lot because it is, but that's just because it's an extremely thorough example. So let's go ahead and look at this. We've got a box of mass 10 kilogram that's sitting on a table. Okay, so in other words, it would look something just like this. You've got a table, right? And you've just got a box, and it's just sitting there, and it's 10 kilograms. And we want to determine the normal force on the box and the weight on the box. Then we want to do various scenarios with it where you're pressing down on the box. So pushing down on the box, lifting it up, and then what happens when a person pulls up on the box with a force of 100 newtons? What's the acceleration? What's the normal force? So step one for every single type of question like this where we're dealing with forces is to draw a free body diagram. So draw free body diagram, okay? And we'll need a couple of these. So the first one will apply for parts A and B. Because what happens is in the other parts, we add forces to them, right? So in part C, for example, you press down on the box, right? That's an additional force, so you would need a new free body diagram for that. Or you pull up on the box, that's a new free body diagram. And then you change what you do in part E. You pull up on it more. So let's just do the free body diagram for parts A and B. Okay. So step one, the box becomes a point particle, right? That's how we treat all objects in this class. They don't really have shape yet. When we get to rotation, we'll start dealing with objects with size. But for now, like with kinematics, everything is just a point particle. Okay. So from that, we start drawing our forces. We start with gravity because gravity is, unless it explicitly tells us not to, you put gravity in, okay? And it points straight down. Now we want to do other forces, okay? So the other forces that we would look at is you go through a list of other forces, right? So there's normal, there's tension, there's pushing or pulling, there's friction, there's maybe springs, okay? And you kind of just go through the list and see if it exists, okay? So for this, the normal force. Well, the normal force exists when the object is touching something, so a surface. Is the object touching something? Yes, the box is touching the table. So the normal force then acts perpendicularly to the surface that it's touching and goes into the object. And you would do it like that, okay? It would be straight up. So we draw this on our diagram here, and we draw straight up, okay? Just to make sure you understand this concept, if you have a box and you're pushing it into a wall, okay, it would have gravity down too. The normal force for this, because it's touching this surface, it would be perpendicular to the surface and into the object. So in this case, the normal force would be like this. If you're on an incline, the normal force would be perpendicular to the surface, oops, and into the object, okay? And you'll see we'll do inclines later, okay? But if it's on a flat surface, the normal force points straight up and goes into the object. Okay, check. Is there tension? Are there ropes? Are there strings? No, no tension. Is there pushing and pulling? Not yet. Is there friction? Friction we'll look at in the latter half of Unit 2, so we're not going to look at it yet, but I will be doing friction examples. And it will be really obvious there's friction. It will say the surface is rough, or there's friction here, something like that. And then springs, there's no springs mentioned. Okay, so this is it. This is our complete free body diagram. Okay, so this is complete. It's complete. There's no other forces. Okay. All right. So the next thing that you want to do, step 2, is you want to write equations. Okay, write, x and y equations. Okay, so in the x direction, so for this, if we draw a coordinate system, right, plus x plus y, are there any forces acting in the x? No. So you can write multiple symbols here. You could write no, or just this. You could write not applicable. You could just write 0. I wouldn't leave it blank. Maybe you want to just do a dash. But my favorite symbol is just that. Okay? So there's no forces at all. Thus, you don't need any equation. In the y direction, there's 2. Okay? In the plus y, you have Fn pointing up. Okay? And so you would write Fn. You could write positive just to make sure. And then you would write minus because Fg is pointing down. Okay. So this is our equations right here. You have Fn because this is positive, and you have Fg, which is negative, and it would be pointing down. The next thing that you want to do is you want to set this equal, because remember, we're looking at our equations look like this. The sum of the forces, which we've just done, equals ma. This is the mass of the box. Okay, so this is the box. And our acceleration of box. But the box is just sitting on the table. Okay, it's not accelerating. So you would write 0. Box isn't accelerating. Okay, so our equation then just becomes this. All right, cool. Now, step 3, solve. Okay. So we want to determine the normal force of the box. So part A, okay, so we want to solve for Fn. Well, you just add over, right? Fn equals f of g. Okay, so the normal force equals the force of gravity. Okay, that's good to know, but what does f of g equal? Well, f of g equals mass times gravity, okay? And this itself stems from F equals ma, where the acceleration is g, okay? So, and this is always true for us, okay? In fact, on a lot of free body diagrams, if people are doing that, they'll sometimes write mg down, okay? Just to denote that instead of f of g. I usually, like I said, I like to leave it as just the force of gravity because it makes it consistent. It tells you it's a force, you know, So what you can now write is Fn equals Fg equals mg. So Fn equals mg. Okay. And this is the mass of the box. This is gravity. So Fn equals 10 kilograms times 9.8 meters per second squared equals 98 newtons. That's part A done. So part A, check. Okay. We now want to determine the, one thing I should mention, just to make sure this is, I don't know, kind of obvious. These guys are vectors. And so when we translate these to the equation here, I get rid of their vector symbol and instead assign the positive and negative. So you don't need to have the vector symbol there anymore because you've already indicated direction with the positive and the negative. Okay. So just in case that wasn't explicit, I wanted to explicitly state that. So you can drop the vector hat when it comes to this, or the vector symbol indicating direction, because the positive and negative do it for you. Okay. So just to recap what we've done so far, we did step 1, we drew it. Step 2, we wrote equations. Step 3, we solved. Okay, and they're very, very consistent with that. Okay. Step 3, B is weight. Whoops. Weight of box. So what is the weight of the box? So the weight is the force of gravity. So weight is the force of gravity. This is why people say, when you travel to the moon, your weight changes. Why does your weight change? Because what comprises your weight, which is the force of gravity, changes. Not your mass. Your mass always stays the same. G changes. Okay, so G is a function of Earth. It's a function of the mass of Earth. And if you go to the moon or something, this guy goes down. And so because this number goes down, even though this stays the same, your weight also decreases. Okay. So your weight's just a function of the planet you're on, or the object you're nearby. Whereas mass is always consistent, always stays the same. So anyway, the weight is the force of the gravity, so the weight in this instance is the same as the normal force. Don't get them confused, they are still different, but in this instance, they're the same. So not always true. Not even close, okay? When we do inclines, they won't be the same. They're typically only the same. Well, you'll see. We're about to do some examples where they're not, okay? So let's do part C. So now, in part C, the FBD, we still have, I'm going to do this. I've got to make it a little bit bigger. You have the force of gravity going down, and you have the normal force because it's still on the table. But now you're pushing down, okay? This is what changes. You're pushing down with 40 newtons. And so this is what your free body diagram kind of looks like. You've got two forces down and one up. So with your equations in your x direction, you still don't have anything, but in your y direction, you've got Fn minus Fp minus Fg. And this still equals 0 because the box isn't accelerating. All it tells you is that you're pressing down on the box. So it just says you're pressing on it. It doesn't say it's accelerating through it. So now what is the normal force? So the normal force, we have to add these guys over, equals the force of the push plus the force of gravity. So gravity from before was, 98 newtons, right? This was just mass times gravity, and this guy was 40 newtons. So this equals 40 newtons plus 98 newtons equals 138 newtons. So the normal force can change, okay? So Fn can change. It's a reactionary force, I guess is a way to think about it. It's not the third body, it's not the Newton's third law reaction to it. That goes into the table. This is just a force that reacts to you doing something. So it's a little bit different. But it's not the Newton's third law version. We'll talk more about Newton's third law in the next section about how that works. But you can think of this as a reactionary force because it can increase, right? If you push on the table, your hand doesn't go through the table, okay? If you push harder on a table, it still won't go through. Eventually, if you push harder and harder and harder, the normal force will keep pushing back up, but eventually the table just breaks, right? But the normal force can increase. It can change. And so the normal force can change. Whereas the weight will still stay the same. So the weight is still 98 newtons, okay? To answer that second question. So this is an instance where weight and normal force are not the same, okay? Because the weight is still, F of g. Nothing about these have changed just because you're pushing on the box. The mass of the box is still the same. G is still the same. So there's that. Let's look at part D. It's becoming a long problem. Part D. You pull up on the box with a force of 40 newtons. What is the normal force now? What is the weight? Okay. So now we have to do a new free body. Okay. You pull up on it. You still got the normal force. You still got gravity. And you're pulling up now. Okay. And again, this is 40 newtons. So in the x direction, nothing. In the y direction, we have f of p plus f of n minus f of g equals 0. These two are pointing up. This one was pointing down. And we want what is the normal force. So f of n equals f of g minus f of p now. So this would be 98 newtons minus 40 newtons equals 58 newtons. So now you've reduced the normal force. And it's true, right? If you pull up on some object that's on a table, you reduce the amount of normal force there. If you pull up enough, you'll eventually lift that object up, right, when the normal force goes to 0. We would have to lift up with 98 newtons for that to happen. And we'll do that in the next part. Of course, Fg equals 98 newtons still, which is the weight, okay? So again, the weight isn't changing, but the normal force is, okay? So they are not the same thing. Part E, I believe we are on. The final part, what happens when a person pulls up on the box with a force of 100 newtons? Okay, so now we're getting to something kind of interesting happening. You have this. You have f of p. I'm going to say there's a normal force, just so you can see what happens. And then f of g. This is 40 newtons. Okay, so if you drew this as your free body, oh, sorry, this is 100 newtons. If you drew this as your free body, okay, what would happen? Let's go ahead and say, it says that it's, what is the acceleration? But let's just say it's not accelerating. So f of n equals fg minus fp. If this were true, so 98 newtons minus 100 newtons. So if you assumed there was a normal force and you're pulling up with more than the weight, you would get a nonsensical solution. Okay? If the normal force is negative, there is no normal force. Fn equals 0. Okay? Which means you have f of p and f of g only. And in fact, you are accelerating. So you would write ma. The fact that you are accelerating is indicated in the problem. Okay? So what is the acceleration? What is the normal force? Well, we answered what is the normal force. Fn equals 0. Okay? So what is acceleration now? Well, here's our equation. We have Fp equals ma plus f of g equals ma plus mg. Okay, here's our equation. And we need to solve for ma, actually. So what I'm going to do is I guess I will subtract this guy back over, because I'm dumb and didn't realize that's what I was solving for, and just divide by m. So a equals Fp minus mg over m. So this was 100 newtons. Mg was 98 newtons. This is 10 kilograms. So A equals 2 newtons over 10 kilograms. If you break the newton into components, it's a kilogram meter per second squared, so the 2 kilograms would cancel and you'd be left with units of meters per second squared, which is the unit of acceleration. So this is 0.2 meters per second squared. Okay. And that's kind of how you deal with these sorts of problems, okay, the pushing up and the pulling down. Let's go ahead and do another one. It was a long example, right? Let's look at example 2. A 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward, or 20% of gravity downward. What is the normal force on the woman during this descent? Okay, so you have a woman in an elevator, right? So she's in an elevator. She's touching the ground. So when we do our FBD, we've got two things acting on her. We've got gravity, of course. Doesn't matter if you're moving up and down, gravity still acts on you. And you have the normal force pointing up, okay? Because she's touching the floor here. And so this will push up into her, okay? There's no other forces acting because there's nothing else touching her. There's nothing else like that. So this is our free body diagram. There's no x forces still. Because, you know, we've got our typical coordinate system here. But when we draw out our equation, there is an acceleration because it tells us we are accelerating, okay? It says we're accelerating at 0.2 g downward. So you would write this as Fn minus Fg equals m minus, it says we're accelerating at 0.2 g downward, so 0.20 g downward, which means this negative. So Fn minus 0.20 mg is our equation, okay? We want to solve for normal force, so we're going to add over gravity over here. So gravity is mg, or here, I'll do it like this. F of g minus 0.20 mg. Gravity is mg, okay? That's what it's equal to, right? Fg equals mg. And you're subtracting 0.20 mg. Okay. So there's a quick way to do this without plugging in mass and gravity for all of this, is if you think about this, in front of this guy is an understood 1 right here. There's a 1 right there. And so 1 minus 0.2 is 0.8. So this would give us 0.80 because 1 mg minus 0.2 mg. And so this will just save us a little bit of time on calculation. 65 kilograms for the mass, 9.8 meters per second squared. And so the normal force for this ends up being 510 newtons, roughly. Notice, one thing I want to point out is notice she's accelerating downward. What happens when you accelerate downward? You feel like you are kind of flying up in the air a little bit, right? What you're feeling isn't your weight changing. Your weight still stays the same. It's your net force that you're feeling, okay? So when you go up and down in an elevator, why do you feel weightlessness or heavier? Your net force changes, not your weight, okay? It's shown right here, right? Your normal force is changing, which is your net force here, okay? So you could just say your normal force changes, right? And if you think about it on a scale, if you stand on a scale, that normal force that points up is what the weight is recorded, okay? Because if your normal force is going down, like this, so it goes from this to this guy, then this also goes down, okay? It's a reflection of that, the force that you exert on the scale, which is the third body, or the third, Newton's third law variant of that, okay? So as that gets smaller, your weight that you record as a scale gets smaller. But your actual weight, your physical weight, m and g, aren't changing. You're still on Earth, so gravity's still the same. Your mass is still the same. The only thing that changes is your normal force. And this is what a scale records. Okay? That's why you feel weightless. This also, if you were to accelerate at g, it would be mg minus mg, and you would have no normal force, and you would be completely weightless, and you'd be floating. That's how it works in space, okay? When you're in orbit, you're constantly in free fall, which means you don't have a normal force, okay? And so, yeah, that's also why you would feel heavier. If you were accelerating upward, instead of subtracting these two, you'd be adding them. And so it'd be like 1.2 mg or 1.5 mg. Okay? So I hope that makes a lot of sense. Let's look at example 3. So this is going to be a two-dimensional example because we haven't done one yet. We've only been doing 1D. So you pull a box of mass 10 kilograms to the right with a force of 40 newtons at an angle of 30 degrees to the right, or at an angle of 30 degrees relative to the horizontal, along a frictionless flat surface. So this is kind of what this looks like. You're pulling it like this, kind of like a thing upwards, okay? And we want to know what is the acceleration of the box and what is the normal force. Okay, so we need to draw a free body diagram. Normal force. Even though we are moving to the right along this surface, we're still contacting it, and we're still perpendicular to that. Okay, it's still a flat surface, so normal force would point straight up into the object. Gravity still points down. We're still on Earth. Nothing's changed there. And now we're pointing up at this 30-degree angle. We can call this just F of P. Okay. And so here's our three forces. We're going to use this as our coordinate system, pretty much like always. We will be changing that when we do inclines and stuff, so stay tuned. But for now, this is what we got. And so in the x direction, we finally have a force. We have the x component of Fp, right? Fpx. So I'm going to actually write Fp cosine theta, okay? So theta, right, if this is the adjacent side, which it is, right, you use cosine for it. Okay, so it's adjacent over hypotenuse. And this equals the mass of the box times acceleration. Okay. We have a lot of forces in the y. We have 3. So what are they? They are, according to my diagram, you have Fn pointing up. You have Fp sine, plus Fp sine theta, okay? And you have gravity pointing down. As for acceleration in the y, there is none, because the box isn't moving up and down. The box is only moving right and left. In this case, just to the right, okay? You pull a box to the right. Cannot, I guess, highlight that. That's fine, whatever. To the right, okay? So, one other thing I want to point out, if you do some force with some component in the x direction, make sure you reflect that with its counterpart in the y. Okay, so if you have Fp cosine theta in the x, you better have Fp sine theta in the y. Okay, you need both if you've got a counterpart. Okay, so what do we want here? What is the acceleration of the box? Okay, cool. So A equals Fp cosine theta. We just divide by m. I think it was 40 newtons. Cosine 30 degrees over 10 kilograms. Yeah. And so what I get from this is roughly 3.5 meters per second squared. Okay. This guy was root 3 over 2, and that's about all I can do as far as simplifying this. You just got to plug in numbers. Okay. We need the normal force next. So the normal force is, let's rewrite that equation. Fn plus Fp sine theta minus Fg equals 0. We need to solve for this guy. So we get mg, right, minus 40 sine 30 degrees. This is 1/2. So it's going to be 10 times 9.8 minus 20, 98 newtons minus 20 newtons is 78. So Fn equals 78 newtons. Okay. So next time we're going to be working on more examples. We're still going to do the same thing in every single problem. We're going to do free body diagram, equations, and then solving. And you'll see a little bit more interplay between x and y. Like we'll solve the x equation and then plug that solution into the y equation. And that will work similarly to kinematics, where you solve for time in one, plug it into the other. Okay. But as far as free body diagrams and stuff, all of that will just be mostly the same. We're just going to be adding more forces as we go along. I think we're doing tension next time and some multi-body stuff. Okay, and maybe inclines. So thank you for watching, and I'll see you in the next one.